All right, today we're going to pull back the curtain on what makes Bitcoin so secure. We're talking about proof of work. It's the secret sauce, really, that lets this massive global network run without any one person or company in charge. So let's just dive right in. So let's start with the big, fundamental question that Bitcoin had to answer. Imagine you have thousands of people all over the world, complete strangers, right? How on earth do you get them all to agree on one single truth, especially when it comes to money? How do you build trust when, by design, you can't trust anyone?
To really wrap our heads around this, we're going to use a famous old analogy from computer science. It's called the Byzantine General's dilemma. Picture this. You've got a bunch of generals, all on the same side, and their armies are surrounding an enemy city. They have to make one single coordinated decision. Do we all attack, or do we all retreat?
But here's where it gets tricky. The only way they can talk to each other is by sending messengers. And, to make matters worse, they know for a fact that some of the generals could be traitors. So a traitor could totally sabotage the plan, right? They could send a message to one general saying, attack, and another message to a different general saying, retreat. Just chaos. The whole goal is to make the honest generals fail. So that's the million-dollar question, isn't it? How can the good guys, the loyal generals, come up with a foolproof plan to make sure they all act together, no matter what lies the traitors are spreading? This, right here, is the absolute core problem of getting everyone on the same page in any system that doesn't have a central leader. Okay, so how does this old story about generals connect to Bitcoin? Well, let's bring this analogy into the digital age. It's the exact same problem, but now we're talking about nodes on a network, and the stakes are, a whole lot higher. So, in the Bitcoin universe, the generals are just computers on the network. We call them nodes. Their coordinated attack isn't about storming a city. It's about agreeing on the one true history of every transaction. That's the blockchain. And the traders? Well, those are bad actors, dishonest nodes, who might try to cheat the system, maybe by trying to spend the same money twice, or blocking other people's transactions. Now, what happens if the traders, these dishonest nodes, actually get control of most of the network's power? Well, then the system completely breaks down. This is the scenario we call a 51% attack. If they control the majority, they can basically rewrite history and bend the rules to their own advantage. So that's the big, scary threat. The question is, how does Bitcoin stop this from happening? How does it solve this Byzantine general's problem? Well, the first part of the answer, the first piece of the puzzle, involves creating a kind of unbreakable digital fingerprint for data. This fingerprint is made using something called a hash function. It's a really cool cryptographic tool. You can feed it basically any kind of data, a single word, an entire book, a list of financial transactions, whatever, and it spits out this unique string of letters and numbers. That string is called a hash. It's like a unique serial number for that exact piece of data and only that data. Let's look at an example. If you take the phrase hello world with a capital W and run it through Bitcoin's hash function, you will get this exact long string of characters every single time. No exceptions. The same input always gives you the same output. But now check this out. Look what happens if we make the tiniest possible change. We just change that capital W to a lowercase w. And bam, the hash is completely different. It's not just a little different, it's totally unrecognizable. This is super important. It's called the avalanche effect, and it's absolutely crucial for how Bitcoin stays secure. So this reveals a few key things that make these hashes so incredibly useful. First, every output is unique, which is great for spotting any changes. Second, it's a one-way street. You can't take the hash and work backward to figure out what the original data was. It's impossible. And that turns the whole thing into a massive math puzzle. You can't be smart and solve it. You literally have to just keep guessing over and over and over until you stumble upon the right answer. It's all about raw computing power. Okay, so we have this amazing tool, the hash function. How does Bitcoin use it to build a trustworthy system? Well, it's not just about making digital fingerprints. It's about turning this into a giant, never-ending competition, a global digital race. And that competition has a name, proof of work. Here's the play-by-play. All those nodes on the network, we call them miners in this context, are all racing. They're using their computers to try and solve that hash puzzle we just talked about. The first one to find the answer gets to shout Eureka and propose the next block of transactions. Now, here's the cool part. While it was super hard to find the answer, it's incredibly easy for everyone else to check it. So all the other miners quickly verify the winner's work. If most of them agree it's legit, that new block gets added to the chain. Done. And that's exactly why we call it proof of work. The winner has to show actual cryptographic proof that their computer burned a ton of electricity and did a whole lot of heavy lifting, that it did real physical work to solve that puzzle. It's a way of proving you've got skin in the game. It's expensive to participate, so you're invested in keeping the system honest. So you might be asking, why would anyone go through all this trouble and expense? Well, because the prize is huge. The miner who wins the race gets a three-part reward. First, they get the honor of adding the next block to the chain. Second, they collect all the transaction fees from that block. And third, the big one, they get a reward of brand new Bitcoin that was just created. It's a very powerful incentive. Now, to make sure this race doesn't get too easy or too hard, the Bitcoin network is super clever. It automatically adjusts how difficult the puzzle is. The goal is to keep things consistent, so that no matter how many miners join or leave the race, a new block gets found on average about every 10 minutes. It's like a self-regulating system. So, let's put it all together. You've got these one-way digital fingerprints, the hashes, and you combine that with this non-stop, super expensive global competition. What do you get? You get a system that's unbelievably secure. You get what is essentially a digital fortress. Think of the blockchain as an actual chain, like with links. The fingerprint of each block, its hash, is literally baked into the data of the next block. This creates this incredibly strong cryptographic link. Block number 100 is linked to block 99, which is linked to 98, and so on, all the way back to the very beginning. It's one continuous, sealed chain. Okay, so let's bring back our bad guy, the traitor. What happens if they try to be sneaky and go back to an old block and change something? Let's say they want to erase a payment they made last week so they get their money back. Well, remember that avalanche effect? The second they change even one tiny detail in that old block, its hash, its fingerprint, completely changes. But wait, that old hash was part of the next block, so now that block is broken. And since that block is broken, its hash is wrong, which breaks the next one. It causes a domino effect. The attacker instantly shatters the chain, and everyone on the network can see it. So for an attack like that to actually work, the cheater would have to redo all that proof of work, not just for the one block they changed, but for every single block that came after it. And they'd have to do all of that faster than the rest of the entire world's miners are building on the real honest chain. It's an impossible race. And this is the most important part. Proof of work makes cheating just stupid economically. The amount of money you'd have to spend on computing power to even try would be astronomically higher than anything you could possibly hope to steal. And you know what? This system has worked. For more than a decade, it's secured trillions of dollars in value without ever being successfully attacked. It truly is an amazing digital fortress, built not on walls, but on clever math and powerful economic incentives. But all that security, all that work, it doesn't come for free. And that leaves us with a really big, important question to think about. What is the real-world price, especially when we talk about energy, of keeping this incredible fortress secure?